Why don't you go ahead and start?
Why don't you start a project?
Okay, I will project. Let me get my screen up here. Share, screen share, screen 2. Do you guys see my screen okay?
Yes.
Okay, Andrea, do you want to give an introduction or should I just start?
Yeah, I think you just start because the introduction is on the first slide. So the event. So we have different. Let's say it that way. We have different events to kind of prepare cloud physics in the future in different topics. So we have one today, which is centering around the in situ and remote observations. We have one which will tackle the modeling issue, and then we have one which is centered around the lab studies that we're missing. And so we are now starting with the in situ remote sensing observations, what we need to measure, where and when and why, and how these missing information will help us to understand the cloud properties. So we have 4 people here on the stage that address these problems from different angles. So we have Greg, who is the in situ measurement person. We have Chandra, who is the remote sensing measuring person. Daryl will talk about some instrumentation necessities, and I can add my grain of salt concerning models. So we have a certain sequence, and Greg is designated to start with the in situ observations.
Okay, well, thank you everybody for attending. And I'm going to give a bit of a broad overview as well as talking about the particular in situ measurements I wanted to talk about. But really, the question that we're proposing in today's session is what properties, in what location and season, and at what spatial and temporal scales do we need to improve our measurements of? And how do these missing measurements impact our understanding of cloud properties? And I put together about 3 slides as a bit of an overview. And first of all, thinking about what do models need from in situ data? The reason I pose this question is because we measure cloud properties, but we also need to learn about processes. We don't make measurements of cloud processes, but rather we need models to get the process understanding. Now, I know Jason just talked about his nice complex model schemes and the PIP schemes in a recent presentation. But we can look at sort of a very simplified version of a model. This is the old Goddard scheme, where you might predict the total mass of vapor, graupel, ice, snow, cloud water, and rain. And then you have a bunch of arrows that represent the transfer of mass that you're getting between hydrometeor categories. Or you might have more complex schemes where you also look at transfers of numbers between different hydrometeor categories or predict properties of these hydrometeor categories. But the bottom line, no matter what model scheme you have, these schemes require information about cloud microphysics to calculate the conversion rate between species. And these will impact things like the latent heating rates, latent cooling rates, radiative heating, which in turn feeds back on the dynamics and evolution of the system. So the things that you need to calculate these process rates include things like the size distributions that might be parameterized, say, as a gamma function. For ice crystals, you might need to look at mass diameter relations, or fall speeds, or scattering properties. So that's a very elementary introduction of how the models and in situ data work together. So what are some of the key geophysical variables we need from an in situ perspective? Well, for liquid clouds, we would need things like vertical profiles of liquid water content and the liquid water path. We need cloud droplet size distributions, extinction, and precipitation rate. For ice clouds, we have a lot more needs. We need to know things like the ice concentration and the size distributions, and we need to know about the ice water content, and also about the mass diameter relations and density, because that gives us some of the single particle information on the mass of particles, which we need to know. We need to know the radiative properties. We need to know things like the surface roughness of ice crystals. We need to know about the relationship of convective properties and entrainment to the cloud particles that are produced. We need to know about the fall velocities, the shapes of ice crystals, the phase distributions for mixed phase clouds. And I'll make a note, special note here, that information on small crystal shapes, sizes, and concentrations, although we've made progress, it's still problematic. And then it's important to note that not only do we need to know about the clouds in order to understand processes, we need to know other things like cloud updraft and downdraft speeds, turbulent fluxes of energy and moisture, aerosols, cloud condensation, nuclei, and ice nucleating particles, thermodynamic structure, and humidity. And another key thing to note is we also need to know about statistical distributions with uncertainty estimates. That's very important, especially as we move to ensemble or stochastic parameterization schemes. And in terms of location, I just put together a very crude plot here where all of the boxes tend to show some locations where we've done experiments. I know this is not complete. I just did some last night that I could see. The important thing is cloud properties vary depending upon formation mechanism, height, geographic location. So we need observations in a variety of locations. But if you take a look at this map, you see that observations over remote oceans are especially missing. Observations over polar regions are needed given rapid changes occurring there. Observations over the tropics are undersampled. And then also, we don't know a lot about convection and coupling of convection to high cloud properties. I go back to this classic paper by Leary and Howes from 40 years ago, where they show properties of convection and the relationship to the anvil. We need to know more about how the properties of convection and the initiation of ice and droplets, the up and down draft structure, and the environment drive the evolution of detrained water mass and how that controls the evolution of cloud properties. In situ observations in convective core are especially lacking, which are needed to evaluate remote sensing observations. And also processes, say, responsible for clouds with high ice water contents and small crystals in oceanic tropical clouds are poorly understood. So next, we'll go to Daryl, who will talk a little bit about in situ challenges.
Yeah.
Okay, thank you, Greg. You've set the stage here for a number of the questions and challenges that I wanted to touch on, and these are a very small subset of actually other things that we need to be looking at, but I just kind of looked at some of the current instrumentation that we have and some of the instruments that we need either more of or different ones. So there's holography, which has been around for quite some time, and there's been some extremely nice work done with holographic measurements, but probably the biggest challenge that we have right now in holography is the amount of time that it takes to actually analyze holographic images. And so we need improved techniques or methodology for analyzing holography. As our remotely piloted vehicles are becoming more popular and more used around the world, we need lighter and with less power needed for UAV cloud sensors in order to be able to instrument them. And as far as I know, I'm only aware of a single attempt to look at single particle charge measurement from in situ measurement in real clouds, and we need to develop more sensors that can actually measure this electrical charge. And even though we have many ice nucleus systems around for looking at filter samples and looking at ice nuclei, there are a number of different nucleation modes that are very difficult to actually measure. And as far as I know, we have not yet been able to put an IN sensor for looking at real-time analysis of IN measurements in a lot of different applications. And then, of course, what we looked at is in terms of looking at particle motion in clouds. That's a very difficult thing to do. But it really is needed to look at fall velocity and the actual turbulent motion of particles interacting with particles and moving around other particles. And then as we move on to what platforms do we need autonomous vehicles that don't require human piloting. And we talk about UAVs, but most of these require an operator on the ground that's actually operating the aircraft. But what we need is one that has artificial intelligence and able to know where to go at any particular time to look for what it's measuring. Lighter than air vehicles, I think the idea of a neutral buoyancy balloon, instrumented balloon that would actually follow air particles in cloud would be very useful and interesting. I don't know if that's being worked on right now. And on the ground, I don't know of anybody that's actually got fog monitors that run around taking fog measurements autonomously either. And just only recently do we have some upsons and downsons for dropsons for looking at profiles of cloud properties as well. So that's just a very small subset, I think, of what we should be looking at. So I'll pass it on now to Chandra.
Oh, sorry. Okay.
Well, can you hear me?
Yep, we can hear you fine.
Okay. That's a tough act to follow after Greg and Daryl. So I tried to wear the um, remote sensing hat, and historically, a lot of the remote. Hello? Okay. Can you still hear me?
Keep going. Yep.
Okay. I thought I heard somebody say something. So historically, a lot of the remote sensing has been on quantification and classification, and those were predominantly driven by civil defense. That is, it's all about issuing watches and warnings. Everybody wants to know um, how much rain fell and how big the hail is, and is it hail or water? And so, because these things have very strong applications, and it was these were easy things to talk about and get supported. But we need to change that and go on to what I call as process remote sensing. The whole business of process remote sensing is a little bit different the way you do remote sensing compared to issuing watches and warnings. And that's where I think fundamentally remote sensing has to, I've been around for enough time now to the point that I can distinctly see the difference between doing civil defense remote sensing and then process remote sensing. We need to observe things at the proper space-time scales. So we need to improve spatial scales of observations with dense networks. Like Daryl said, like many things, remote sensing instruments have become smaller, cheaper, so long you're not trying to cover the whole country with one big, giant military industrial scale radar. You can build smaller things, and there is advanced technology coming from electronics completely developed by other industry that it's able to do this. And we have actually shown that with some simple demonstration. And then we can't just do this 5-minute update that is meant for civil defense. And then we have to, there is a fundamental connection between space-time scales and the processes. Like hurricanes are thousands of kilometers wide, and then they last for several weeks. So, but there are small convective processes and even civil defense applications. F1 tornadoes, they appear and disappear within a minute. So the standard 5-minute time scale won't even work. And then the next thing is, this is for some historic reasons, there is a separate, there's sort of separate communities on cloud and precipitation remote sensing. And that's because of it's separated for different reasons due to technologies and then frequency allocations and so on. And we need to bridge the divide, and it's happening to some extent naturally. And then we need to start observing the cloud and precipitation processes together, because again, it's easy to go after the shiny object and high impact event, but we forget to observe the processes. Then everybody has made comment about density of ice in both in situ. In my previous life, I used to work on density of ice with when T-28 was still flying, and then I got off that field for a while, and then a few years ago I tried to get back. It's amazing that how that field has not moved an inch. Again, I'm making this comment from a remote sensing perspective. So that's a huge unknown, and there are process techniques available, and that's something where we can invest and then start looking at more impact on density observations remotely. Then plus I have a lot more things I can say, but I'm going to stop now and hand it over to the next person. Thank you.
Okay, I have hopefully unmuted myself.
We can hear you fine.
Good. So now from the modeling point of view. Greg already gave a good overview of things that the modelers need. So I will not repeat that, but just highlight two things for me that are the most urgent ones. So he mentioned the importance of processes. So processes is difficult to study them in the field. So a lot of that will be done in lab studies, but still, I think that the observations can contribute on understanding the processes because of identifying their location via in situ, but also I agree with Chandra, the remote sensing and the multi-frequency will be very crucial for that, to see where these processes are happening, things that cannot be found in the lab study. So we have still a lot of uncertainties on the multiplication of drops by a breakup. And then obviously that was mentioned several times, the ice phase. That's the big problem here. I just picked out the ice formation, but I agree the density and form are all problematic and are located to well, depend on the location, let's put it that way, in a cloud. So that's one big block where I see the need for where the observations really can contribute. The next thing is the block on the variabilities, because the models, well, will never be as high resolution as nature. So we have grid boxes of a certain size, and well, I don't want to take the thunder from the model discussion section later this week, but there will always be a certain averaging over a grid space. And the question is the real small scale variabilities, will they dominate? I mean, do the model, the mean values of the model, are they sufficient in which way to represent what's happening on the small scale and to what degree the small scale variability will, to what degree we need to take it into account. How much do we have to know on this smaller variability to be correct on the larger scales? And so for me, these are the two questions I would, if you ask me to rank them, I would ask these to the in situ and remote sensing observations. And then I added two questions which are more in a general thing, which I see coming up in the future, which will be addressed to models. but will kind of percolate down or to also the observations, which are the clouds in a changing climate. Will clouds change in a changing climate? A question which will be very difficult to observe because clouds are, per definition, rather short-lived. But one approach which is possible, take different campaigns that we did, big campaigns in the past. I mean, here I did some history. So we have very big campaigns in the 70s, 80s. And would it be good to redo them and by comparison and analysis, maybe get some information? Are the clouds changing in different locations in a different climate? And the other question or um, challenge which will be um, put before modeling is not, well, first maybe modeling, but behind that is certainly the observation, and uh, maybe more direct still is the manipulation or trying to manipulate weather, so weather modification. I already mentioned that because I see it coming up very strongly, not in Europe so much, but it's certain parts of also the US, but certainly in Asia and in Africa, we have a lot of these campaigns of weather modification are coming up. China is very big, Russia is very big. And so are we prepared to address this topic? Because at one time, well, we are at the center, so the questions will be addressed to us. So what will be our reaction with respect to that? Okay, so these were just some my input, and Greg, you can.
Okay, so what we would like to do now is we don't want to talk the whole time. We've got 35 minutes left. We would encourage people to come up to the front of the room and add some discussion or add some points to consider or pose questions. But the main discussion points we want to talk about are: what quantities do we need to measure? Did we miss some in what we talked about? What observations are most needed missing? Are there locations we need to go to plan maybe international collaborative future field campaigns? What spatial and temporal scales or observations needed at? And what phenomena are we not understanding due to a lack of measurements? So please feel free to come up to the front of the room here, and we welcome all of your points and comments. So please don't be shy. Come on up. And I think George is on his way up. So George, please unmute yourself. Yes, we can hear you, George. Go ahead.
We can hear George.
Okay. Oops, you just keep going up and down.
There we go.
You're there. Perfect, George. Okay, start again, please, George, so everybody hears you.
So to what precision are measurements necessary? Because, in the climate models, a few percentage change in the global cloud cover is enough to offset global warming. I think it's around 10% in some microphysical parameters like liquid water content or droplet concentration. That would be enough to offset global warming. So we have to get some idea of what precision is necessary. And they're really demanding measurements. I also want to emphasize the scale. We have to make measurements on the right scale if we're going to compare it with models. Most climate models, like maybe 30 kilometers, we have to make measurements on a 30-kilometer scale. We used to make measurements by shooting a
Can I
slide
go
through a
inside,
slit
please?
and measuring droplet concentration that way. By the way, those droplet concentrations are still used by modelers around the world today, perhaps more than our sophisticated measurements we are using. And I guess the third point I want to make is precipitation. We don't really measure precipitation very accurately. Snowfall measurements are horrible. Um, and there's not much drive in this community to make good precipitation measurements. You can make all the remote sensing measurements you want, but you have to interpret them what they mean. And that's a big challenge. Sorry for ranting.
Okay, no, thank you. That's very, very helpful comments, and that's exactly what we want to hear. And Martina, did you have something you wanted to say?
Yes, I wanted to add to the needed observation the vertical velocity. And because, you know, vertical velocity drives many processes. It drives the Bergeron-Findeisen process, and so it determines the degree of glaciation in mixed phase clouds. It also in cirrus clouds. It determines the competition between heterogeneous and homogeneous freezing. In warm clouds, it determines the number of cloud drops that appear. So I think in global models, it's not very well represented, the vertical velocity, the parameterization, and but also in process models. We do our very best. We need to know the distribution of vertical velocity and also the small scale variations. I think we would more better with a better knowledge of vertical velocities and ice nuclei and ice nucleating particles. Yeah.
Okay, thank you very much, Martina. Alexi, please come up and sit on the sofa, and the microphone is yours.
Yeah, do you hear me?
Yes, we hear you, Alexi.
Yeah, thanks. So I want to say one of the big caveat of existing measurements is very small sampling. Out of few cubic kilometers or 10 kilometers, cubic kilometers clouds, we are sampling only few liters. And after that, we are trying to judge, and using this little one, we try to just restore the entire dinosaur, and it may lead to completely different conclusions. And my point is not practical at that stage, but we have to look over the horizon, that we have to start looking for new generation of instruments and using new physical principles, and they exist. And so which allow increase sampling volumes, orders of magnitude, to increase, to make the sampling statistically significant. So that's my point, and we have to probably send a message to funding agencies about that. So we have, because we almost explore to the end existing technologies of sampling individual particles, and so and reach the ceiling in our measurements, in quality of our measurements, and how much we can get out of it. Thanks.
Thank you, Alexi.
Greg, can I add to Alexi's point?
Certainly, go ahead.
Yeah, so Alexi, I think you were talking about increased sample volume of in situ instruments. And is it possible to think about looking at it in a different way rather than a large sample volume from a single instrument, actually sending out a swarm of instruments with smaller sample volumes, but sampling over larger volumes with a number of different instruments so that in the long run you get a larger volume?
Yeah, this is one of the way of doing this, and so that, for example, some instruments are attempting just increasing number of beams, but eventually you increase it twice, maybe 4 times, 10 times at most, if you just put all those instruments around the airplane. And I'm thinking about just some techniques, and based on kind of existing new other physical principles, which are in between of remote sensing and local remote sensing and the situ sampling, which allow you characterize in quite different way the sampling of clouds.
Okay, if someone else has more comments, there's lots of spaces on the red sofas. Please come up and just sit on the red sofa, and we'll be happy to turn the microphone over to you.
Who is speaking now?
Okay, Peter, go ahead.
Hi, so just like
I
as
cannot
a
hear him at all. I
as a
think this is
general
the problem
comment
now.
for
This is the problem, and we have to move some people in the other room.
Yep, Peter, go ahead with your
what?
general comment, please.
So I just like for I was thinking about like in terms of how where like areas we need to do some research and work on in cloud physics. I was thinking about how like one of the biggest areas of uncertainty with global warming is cloud feedback. So I was thinking it would probably be a good for us in cloud physics to work on trying to improve cloud parameterization, particularly with respect to radiative forcing, and let's see if we can figure out how to make the increase numerical confidence in the climate models on clouds.
Okay, yes, that's a good point. And related to that, are a lot of uncovering what are the cloud radiative properties. So for example, that factors into many different aspects in terms of, do you use mixtures of different particle habits to determine what are the cloud radiative effects? Or do you use some sort of surrogate model that is designed to represent the radiative effects? With regards to, say, surface roughness, which is something that is very important in determining the radiative effects. We've never actually had very good measurements of surface roughness. Rather, we've just indirectly measured what are the radiative properties. So there are a number of different questions there that could be asked and measured to try and improve the radiative effects. And I think the fall velocity also has a big impact there, because that will impact how long the clouds last, which in turn also has a big impact on the radiative forcing. So good point.
Hey,
Thanks.
Greg, can I add a comment?
Certainly, Chandra, go ahead.
So there's one point I missed in my slide is things have moved along so well. I think we should start paying attention to mixers, because a mixture is sort of totally ignored. I shouldn't say totally. As soon as I say totally, somebody would have worked on something. It's not, we don't pay too much attention to mixtures in remote sensing and formulate them that way. And that's an important point I like to add there.
Okay, yes, good.
Hello. I wonder if I could make a contribution.
Certainly, Vaughn, go ahead, please.
Hello, Greg. I found Andrea made a very interesting point about looking at long-term climate trends of cloud observations, particularly from these looking at past campaigns. And it seems to me that there's so much change in the accuracy and in the biases of the instruments used over from decade to decade. I think there's something to be said for trying to move towards a sort of standard with some of the instruments, so that we can be sure of using the same instruments over multiple decades in some of these field campaigns. So then, with the same instruments, one could compare campaigns in different decades and have some hope of detecting a trend. So the problem at the moment is that if we go back to gate, for example, the biases in measuring vertical velocity, for example, are going to be completely different to the biases now with different instruments. So I think it's a really good idea. Maybe we can try to think about standardizing some techniques of measurement, some types of instrument. And just one other unrelated point, one other point I'd like to make is that I think there's too little funding going to lab observations for specific processes. So I think that I think we need to invest much more in lab observations of, for example, secondary ice production. And if one takes as an example the Hallett-Mossett process, something really amazing is that 3, 4, 5 decades have passed since the Hallett-Mossett experiments in the 1970s. And almost nobody has tried to reproduce those observations in the lab. So that's just one example, but there are many secondary ice production mechanisms that have been completely unexplored in the lab. And at the same time, our focus as a community seems to be entirely on the modeling or on the remote sensing or on the field observations. So there seems to be a blind spot, I would argue, and that blind spot is lab observations. So anyway, I'll stop there.
Okay, well, thank you very much. One point I will note is that on Friday, Alexi and several others will be leading a panel discussion on lab experiments. So we can talk a lot more about the lab experiments on Friday. But I see others are coming and wanting to make comments. Thara, did you want to make some comments here?
Hello everyone, this is Tara. I think I have some connectivity problem.
Okay, we'll let that. Daryl, did you want to respond to some of Vaughn's comment as Thara works on her connectivity problems?
Experiments, we need new sensors and instrumentation to make those laboratory measurements as well. And we'll talk more about that on Friday.
Yeah. And one other point in response to Vaughn is that standardization over decades is going to be very tough because there are continual improvements in the instruments. So, you know, we want to take advantage over obviously, you know, what improvements or enhancements are made in instruments, but at the same time, there is an argument for continuity. So it may be that we need suites of sensors so that we can maintain some of the continuity with the instruments, but at the same time have some of the newer improved instruments available for comparison. So I see others are coming up. Thara, do you have some comments you wanted to make? Are you connected now?
Can you mute that? Sorry about that. There are some feedbacks in this room. Let me fix this first.
Okay, are you're under Mahen now, so I assume that's you coming through Mahen's name. So
Yeah, because I had problem with my computer, so that I could not say anything there. So
okay, well, I think we can hear you now, so go ahead, please.
Yeah. Now it is clarified. But just one couple of points I wanted to make. One is regarding right now I see that much of our focus is also going into second order parameters like um, the dispersion and various other also the spatial variability within the clouds. So we are indeed many of the observations now or the instrumentation whatever we are having, it is under a particular limit where we cannot even see mean we are looking at, but standard deviations also we are looking at right now. But, these are very big quantities now. There are no instruments that are indeed right now available in order to look at such second order parameters. So another one point is that, and another point is regarding we have worldwide several observational campaigns are going on, and there is no unified consortium or an arrangement made between different nations or different. Actually, ICCP has a potential to bring something like that in the future, so that many of the observations that are done can be brought together to into one umbrella, and that could indeed help the modeling community as well to use that and make progress. So I just wanted to mention these 2 points. Thank you.
Okay, thank you very much, Thara. I want to make sure there's opportunity for everyone to speak who wants to. Is there anybody else who wants to come up? Please just come up and sit on the red sofas and unmute yourself. I'm not sure if those standing at the right-hand side of the stage are just standing there or they want to say something. So if you want to say something, please just move on to the red sofas. Okay, well, one thing I'll say in response to Thara is that, you know, it was unfortunate that we were not able to conduct our cloud probe workshop, data processing techniques workshop before this meeting. We had originally planned to do this the weekend before. This has been an initial step that Daryl has been most instrumental in trying to, you know, at least bring the community together to talk about ways of trying to get our data processing done in a common way and better understanding the uncertainty characteristics of some of the instruments. And it's something we certainly need to do a lot more of in order to advance the science, and also starting to bring the data together from several different countries. So it's something we want to do more of in the future. So I see Joanne is coming up. So Joanne, please go on the red sofa so everybody can hear you, and let's hear your point. Please just go down a little. Yeah, now you're on the sofa, so everybody should be able to hear you. Please go ahead.
Okay, you can hear me, Greg?
Yes.
Okay, great. Oh, yeah, take me some effort to get here. Okay, yeah, as I was watching live, and then I see, you know, there's a lot of discussions about the detailed observation, the parameters we need, and it's very grateful. And but I want to emphasize something which is about the model data integration. And as a modeler, I often feel it's very challenging to use those observational data, particularly in the cloud and the precipitation field, because the model simulates very different cloud and precipitation properties with a large variation. And the observation, the same thing. We have often have this large range of the values, and how representative from the observation, and how do I compare fairly with the data. So this, I feel it calls for community effort in the cloud field to build such kind of model data integration to help the modelers can easily evaluate their model and also their parameterizations with observations. For example, building the matrix, some standard matrix, and then also because the modeler a lot of times they don't understand the observational very well. There's lots of caveats. So I feel different people, when they use different data, they have different results about the same observational data. So then that is something I want to emphasize. Maybe the community can do. In other community, for example, the land atmosphere interaction, they have such benchmarking comparison, which is very helpful. Yeah, that is what I want to say. Thank you.
Okay, thank you very much.
So Greg, can I make a comment, or can I respond to Jiwen?
Certainly.
So I encourage modelers to go into the field, go on field projects, be there when the measurements are being taken. It's a totally different experience. I'll never forget when Marsha Baker went to Hawaii with us during the Hawaii project in 1985, and she came back from her first flight. She said, "Now I know what a cloud looks like." And this is what we need as a modeler to understand better how the measurements are being made, what problems there are in making the measurements, and you gain a whole new perspective when you do that.
Yeah, Alexi.
Yeah, in addition to my previous statement, I want to kind of make a comment regarding missing or almost missing parameters from in situ measurements. Those are interstitial CCNs and INPs. So it's kind of, there were several attempts in the past to do it, but it's not much information about what's going on inside cloud. And I think it's a very important measurements, which we have a good number of good reasons to think that these are very important parameters. And for like secondary ice nucleation inside cloud and of CCNs and is especially about INPs. And another thing we just Daryl briefly mentioned about this is we completely missing study of cloud electricity and charging of particles, external electric fields. It was a kind of one of regular measurements in the past of electric fields, but nowadays I'm not sure just who is doing this on a regular basis. And so we have to pay attention because cloud electrification plays important role. Thanks.
Thank you.
Dear colleagues.
Yeah, I would like to reply to Daryl and to Ji Wang because in fact I like the proposal of Daryl to go on the field, but I think it should be a reciprocal thing because it would also help if the experimentalist sometimes touch a model, knowing how their data could enter a model. I mean, just one example is that a model often is initialized by a cloud-free state. And you go out measuring, there is the cloud. And so now we are confronted as modelers to invent a state without a cloud to initialize our model correctly. And in particular, if you talk like CCN, INP, and everything, we need to give this as an initial value, but the measurements that you take, they're already influenced by the clouds. And so this is very difficult. Yeah, to derive or invent the distributions without clouds or some imaginary states prior to clouds.
Okay, thanks. George, did you have some more points you wanted to make?
Yeah, I wanted to bring up the fact of cloud chemistry and its importance, even it's important for air quality, obviously, in any long range transport. Aerosols and pollutants go through clouds several times, but they also are processing aerosols, and they could be making better, more improved CCN, or they could be destroying CCN, or the same for IN. So people should not forget that. It's a wildly open field.
Okay. Thanks very much. That's another good point. Nikolai, did you want to make some points? Just please sit anywhere on one of the red sofas, and then everybody will be able to hear you.
Sorry. What should I press?
Just move down to be on one of the red sofas, because that way everybody in the room will hear you. So just sit beside it.
Red sofa?
Yeah, just go up a little. Okay, you're there. Okay, go ahead, please.
Dear colleagues, we have spoken on in situ data, on microphysics and electric characteristics, but the first in cloud formation is air dynamics. Microphysics is the second. The first of all is convection initialization, is disturbance of temperature field. So we need in situ data on temperature field, two-dimensional temperature field all over the Earth surface. I don't how to obtain this data, and nobody knows. But when initializing model, we have to use parameterization. We use parameterization of McNider and Kopp, temperature field disturbance, normal distribution. There are a lot of parameters. We take it. We don't know how to obtain it, but we need for each time temperature distribution all over the surface to initialize cloud convection. Well, this is the main problem.
Okay, well, thank you very much. That's a very good point to make. Graham, I think, would you like to comment?
I would like to comment. I'd like to pick up on George's point about chemistry. It's interesting. I think it was probably back in the late 90s or maybe the early 2000s that ICCP started to include a large component of chemistry, and aqueous chemistry became something, it became a significant part of our discussions. And I think that's probably not the case today, but I haven't checked the schedule closely enough. The point I really would like to get at is that chemistry can be used to help us understand cloud processes. And I don't think we're doing enough in that regard. I'll give you one example. If one looks at something really important like precipitation efficiency, you really struggle to quantify that. Certainly observations are particularly difficult. One is looking at moisture convergence and measuring volume of water reaching the surface, very difficult to quantify. But then you realize that precip efficiency is very tightly related to scavenging efficiency. And now you can start looking at removal of soluble gases as an example, and of course, aerosol mass. But I think there's a lot to be done, a lot to be explored in the realm of using chemistry, and I use that very broadly here, that term broadly, but I think using chemistry to help us understand cloud physics and precipitation physics. And there are lots of other examples, but that's just one.
Okay, great. Thank you very much. We're coming up to about an hour into our panel discussion right now, and I know it's been a long day, but I want to make sure that there's an opportunity for anybody who has any more points they want to make those. I think I have been taking some notes on all of this because as the new commission comes in place, we will be thinking about workshops we want to do, special sessions at various conferences, and ways that we can try and promote or enhance some of these activities. Obviously, we're not a funding agency, but there are things that we can put out there that we can supply funding agencies with to say, these are important problems that you may need to deal with, and workshops that we may want to have. So we can make a difference. We can have some influence, even though we don't have any direct purse strings. So just before I wrap up, I'll give one more opportunity if anybody wants to say anything, or do any of the panelists want to make any final points?
Greg?
Go ahead.
Yeah, I wanted to reinforce what Nikolai said. And that's that one thing I didn't mention is we can't measure supersaturation in clouds, and that's critical, and yet we can't. And the second thing is, like you said, we've got a lot of topics here, and a workshop that brings modelers and observationists together to do exactly the type of things that Andrea and Jinwen and others were talking about would be a good first workshop for this new commission to support, I think.
Okay.
I totally endorse this idea of modelers and observationalists coming together. That sounds like duh, but I myself hang around with modelers and I learn a lot of things.
Yeah, well, I think that's a good point, because in terms of uncertainties from an instrumental perspective, maybe we can quantify uncertainties in our instrument. But I think, as George talked about at the very beginning, we also need to have a good idea of what uncertainties or what do we need to strive towards in order to get these observations. So I think I'm listening very closely, and I think model observation workshop, thinking about that, maybe as early as next summer if travel's possible by Madison, by the time of the Madison AMS meeting, or if not, the Berlin 2023 meeting. I see, Peter, you're back. Do you have some comments you'd like to make?
Yeah, so I was going to address how it's like I know we don't know much about wildfires and wildfire smoke. I think that's a key area for improvement, and I think also like the intersectionality between wildfires, wildfire smoke, and cloud physics.
Yes, that is a very good point. I can speak as the director of the recently awarded Cooperative Institute in Severe and High Impact Weather Research and Operations in the United States, that one of the areas that we have been given a charge to expand into is wildfire weather, because obviously in the US, we see the extreme impact of wildfires, and this certainly is not restricted to being just a US problem, but especially with climate change that is occurring. The frequency of wildfires will change, and this is definitely an area that will be another area of increasing importance. So, good point.
Thanks.
I see some others at the.
Yeah,
Go
there
ahead.
are the two chat people that want to make
Oh.
comments. Did you check the chat?
Oh, no, I did not. Okay. Stanislaw, go ahead, and then we'll go to Sachin next.
Hello?
Yes, we can hear you.
I can't seem to turn on my camera, but I wanted to only make a short comment about microphysics. So I think we need to work on a way to measure H2O molar ratio or water content in a very fine temporal scale, finer than 50 Hertz, finer than 100 Hertz, because that way we can really understand the microphysics in clouds. And it's just a short comment. Thank you.
Okay, well, that's a short but very important comment. And looking at H2O ratios as well can be important. Sachin, did you want to talk about 2D versus 3D observations? Please go on to one of the red sofas so everybody can hear you. Yeah, you can just go up a little and sit on the sofa there. Yeah, perfect. Go ahead, please.
Yeah, so my question is just when we plan a new field experiment, so how to prioritize the 2D observations versus a 3-dimensional?
Well, I think that question can also be related. I'd be interested to hear what Chandra might have to say there, but I think a key there is that we need to take the advantage of the synergy of both remote sensing and in situ observations. Unless you have a swarm, say, of UASs, it's going to be quite difficult to get 3D observations in situ, but with some appropriate scanning remote sensors, you might be able to get more 3D information. Does any of the other panelists have any comments they want to make on that?
Yeah, Greg, can I respond to that?
Certainly.
I'm glad that comment was made. There was a culture in the old days, as this actually comes in the class of lab experiments. It's not real lab, but it's a controlled experiment where you do in a controlled environment a small remote sensing device and the in situ device looking at the same volume in multiple directions. Because nowadays, the way the connection is made between in situ and remote sensing is you'll be very happy if you can remotely sure that the measurements were made within 10 minutes of each other, or it's even made on the same day, and we throw statistics and probability matching when we don't know how to do careful experiments. So that culture was there, and it was in the original days when people were starting to study the scattering from hail. So I think we can go back to that mode, because a lot of the low-hanging fruits we have already harvested. We need to climb the tree a little further now. So, and I'm trying to wave my hand here, and I don't know if people can see me, but you make an in situ volume and then shine remote observation scale down at the same volume to make sure that you are measuring the same thing. And this type of sort of labish experiment is needed to solve the density problem, leave alone all the 3D stuff. Sorry for a long rambling on that critical point.
Okay, great. Well, thank you very much. I see Graham's coming back. Please go ahead.
Think a little how we do this. And of course, it depends very much on the science questions that we're asking. And I felt that the discussion here today has been a little bit broad in the sense of, we need to measure, and here's a long list. And I think focusing on science questions is a more sensible way to go about doing this. And one way to do this when you're comparing models and observations is to take geophysical variables of interest and set up state spaces that could be two-dimensional, and that of course is easy to visualize, but it could be 3, 4, and n-dimensional. And think about visualizing your model output in that state space and looking at how it evolves in that state space. And alongside of that, doing the same thing with your observations, with all the differences that occur between your model and your observations. The question then becomes, can you identify evolution in that state space in both the models and the observations? How well do they compare? Where do the sensitivities lie, the scale issues, the model deficiencies, etc.? But I think unless we find more compact ways to compare models and observations around particular scientific questions, we're not going to, we're always going to be looking at a bunch of dots that came from an aircraft flying through a small sample volume, and we're going to look at model output and we're going to say, yes, it looks kind of okay. And I think we really should be going way beyond that now. And I don't mean to be disparaging to all those efforts, because they really are difficult, but I think there are better ways of doing it.
So Greg, there's a couple more comments out there from, we just got one that we'll take a look at.
Oh, yeah, there's a couple comments on chat. One from Sriyashi saying, is there any possibility for chemistry simulations to improve precipitation? If yes, why? What could be the possible reason?
Sounds like a question for Graham.
Yeah. Graham, do you want to come back up and see if you can help us with that one?
Well, I guess the example I gave was very much about how chemistry could improve understanding of precipitation efficiency. But if you think of the basic definition of precip efficiency, it's, at least in our world, it's volume of water normalized by the amount of water condensed. Sorry, volume of water reaching the surface normalized by volume of water condensed. Well, if you think about measuring the volume of aerosol scavenged, normalizing that by the volume of aerosol activated, you can see the parallels over there. Now, it doesn't mean that the scavenging efficiency is necessarily an easy measurement, but now one can start getting into soluble gases, not only aerosol. And I think that there are ways to bring the differences between soluble gases and insoluble gases as a sort of background reference, the ratios of these, the kind of enrichment factor approach. This is my thinking anyhow, and obviously it deserves a much longer discussion.
P2021 at IITM. Okay, so here we are, Karim. Oh, what is it? I'm here. Oh.
Okay, Luis, yeah, do you have a point you want to say? Go ahead, please.
No, sorry. I was just a mistake. Excuse me.
Oh, no worries. Okay, we have another comment in the chat from Fontaine. I assume that's Emmanuel. I am thinking about an in situ measurement campaign in convective thunderstorm genesis with measurement of CCN and IN before, during, and after, and follow the development of the systems with with X, Ka, and W band. This combined with cloud measurement probes and IKP measurements of bulk mass would be a good idea. And yes, I think that sounds like an excellent idea. There is some of that which will take place. There is a number of field campaigns taking place in the vicinity of Houston, Texas next year. sponsored by the Department of Energy in the United States, National Science Foundation. Those are the tracer and escape campaigns, which has a lot of those type of probe measurements, and perhaps there's other efforts ongoing doing that type of thing too. So, you know, definitely that's one type of science question that's there. So, Martina.
We just last week we finished an in situ aircraft measurement campaign in mid and high latitudes in lots of convective, mostly cirrus, but also mixed phase clouds. And Andrea, what we also did always, we flew below, above, around. All the information in clear sky. And yeah,
but it's not really, I mean, it's influenced. That's what I'm trying to say. There is no prior because it was already processed.
Yeah, but we do also profiles, and we flew dips to lower altitudes, and we measure CCN, INPs, and gases. We had lots of cloud probes, and for sure you will see the results of this campaign. And yeah, hopefully all the data, we try to provide all the data in a shape so that they can be used by modelers. Mm-hmm.
Okay. Well, in the absence of any further comments, I think we've had a very good discussion to get things started here today, although this is certainly not the end of the discussions. We've got a couple of other interesting event discussions coming up for the rest of the week, which will be as equally interesting, I'm sure. And I think there's a lot that the new commission can take from what we've talked about today, and you can be looking for future workshops on some of these topics. We'll try to always do them before or after some of our other meetings because you know, we don't want to increase travel costs for anybody. It's probably much easier to extend a trip a day or two. It's going to be much cheaper for people than having a separate meeting. We also may look into the possibility of some virtual workshops. So don't be afraid to contact me or any of the other commission members if you have some good thoughts for workshops that we might do, so that in addition to doing your individual funded research projects, we can think about ways of better coming together as a community to address some of these really pressing science issues. So Andrea, do you have anything beyond that you want to add to close out this session?
Except then thanking all those contributors. I think this was really a very exciting meeting. And you know that this was recorded, like all the other things that are going on this site. Everything is recorded and will be put on YouTube, so you can look at it again at your leisure. And also we will put the links on the ICCP webpage so that in case you lose them, you can go back and look at things and remember. So thank you.
Okay.
Thank you.
Thanks, everybody. And we'll see everybody at 12 UTC tomorrow morning, afternoon, evening.
Thank you.
Bye. Thank you. Bye-bye.
Thank you. Thank you, everyone.
Thank you.
Yeah, so thank you, Chandra.
I'm trying to get up from the sofa. I don't know how to do that.
Or just with the flash the arrows on your keyboard, you move.
I am clicking on myself. Oh, looks like I got up. I don't know what I did to move forward. This is